Hello, everyone. It's my pleasure to introduce Hema Srinivasan, who will give a talk on Sally-type numerical semigroup rings. Hema.
Thank you, Reina, and thank you for this opportunity to give a talk in the Fellowship of the Rings. I do have some rings in my title. So this is, I'm going to talk about what are going to be called Sally-type numerical semigroup rings. So I hope it's okay that I have already typed it up, most of it. So I'm going to read off of some of the things, and some I will write on the thing. So I put this down, even though this is not going to be so much of the talk in the beginning, as one question is, if you have something that is a curve going from t to the a1, t to the a2, t to the an, when is this a parameterization of a Gorenstein monomial curve? This is a question to ask. I mean, it's a motivation question. We may as well assume then, without loss of generality, that these numbers, a1, a2, an, are relatively prime, because I could just divide out by the common factor. So for just the next couple of slides, I'll say this curve is C with this A at the subscript, which is understood to be A1, A2, AN. The coordinate ring of CA is going to be a polynomial ring in these n variables, mod out by IA, which is where it becomes homogeneous when we put the degree of xi to be equal to AI. So that IA is the ideal defining the curve. So for that question, when is it a parameterization of a Gorenstein monomial curve? A simple but not really deep or illuminating an answer is that it is true even the semigroup A1, A2, AN that is generated by these numbers is a symmetric numerical semigroup. That's because it is Gorenstein if and only if this semigroup is symmetric. So let's just go ahead, and that's essentially when I say it is not illuminating, because it's the same thing as asking when is this symmetric. So let me tell you what it means to be symmetric. A number is called symmetric if there is a number that's not in the semigroup, such that for all integers x is in S, if and only if f minus x is not in S.
Not yours. I'm not seeing what you're writing.
Oh, really?
Ask them if anybody sees it. I'm not seeing it. Maybe there's something wrong with what I'm doing.
I haven't written much.
I'm seeing
Capital
it. I only see the blue S.
You said the blue S.
I see the blue S.
Yeah, he's seeing it.
Okay, so you see
That's
this
all there is to see, I think.
Yeah.
Okay, all right, now.
Okay. All right. So that number F is a special, it's called the Frobenius number of S. Since the study of monomial curves the same as studying of these numerical semigroups, I just mentioned that in a way of bringing people in who are not into semigroups, that it's symmetric or not, we will just set up some notation for just talking about semigroups. The next one has something to do with the monomial curve still. This is because we are going to talk about it much later on. I asked the question, when is it a Gorenstein monomial curve? When you take this A1, A2, AN as an arithmetic sequence, where this A1, A2, AN form an arithmetic sequence, and A1 is equal to 2 mod n minus 1, then, and only then, it is a Gorenstein curve. So this gives us one way to construct many, many, many Gorenstein monomial curves. And also we can, if you give me two Gorenstein things, then I can create another one by gluing those two things, which means I just take D times one of them and E union with the E times another one, B, where I pick a D that is in the semigroup generated by B, but not in B. And then I take an E, which is in the semigroup generated by A, but not in A. We won't see this construction after this in this talk, but this is just to say you can, that you can create symmetric semigroups in this fashion. And we will create some other symmetric semigroups today, which are not in this fashion. Talk about later on. So let me set up some of the notation for our numerical semigroups. I start with this set of relatively prime positive integers we mentioned, and this S will be the semigroup or a submonoid generated by them. A numerical semigroup is a submonoid of natural numbers generated by a finite number of relatively prime positive integers. We also will assume these guys minimally generate the numerical semigroup from now on. So there are several invariants of interest which help us to understand, classify, or study the numerical semigroups. And I thought I'll mention some of them.
By relatively prime, you just mean all of them together don't have a...
Yes, they don't have a common factor, all of them together. Yes. Now, I take them in ascending order. I always will write them in ascending order, A1 less than A2 less than AN. So the smallest positive integer in S is called the multiplicity of S, which is the multiplicity, as we know otherwise too, of the ring. And the minimal number of generators that generates the semigroup S is called the embedding dimension of S. And that's because when I write it as the semigroup ring, it is going to be Kx1, X2, Xn modulo that ideal of A. Right? Sometimes now I write ideal of S. So all but finitely many of these positive integers are in the semigroup generated by them. And f of S is the largest integer that is not in the semigroup, and that's the one that is called the Frobenius number. Sometimes, even though not for us, not paying much attention to this f of S plus 1 is called the conductor because it's the smallest positive integer. I mean, it's the integer that is one more than the Frobenius number. The next one is called the genus of S. This is the number of positive integers that are not in S because it's a finite number. They are also called the gaps. That's also for the genus or the gaps. These are usually the invariants. And now we have the other one called the width of S. That's the difference between the AN and A1, the largest and the smallest number amongst the minimal number of generators of the semigroup. This is called width, and we will see why it played any role. Then there is this type of S. That's what is called the number of pseudo-Frobenius elements, which is also the same as the Cohen Macaualay type of the semigroup rank S. I think that, I have one more thing. Well, since we have the ring, we also have the Betti numbers. Those are the invariants of the semigroup and the of the semigroup ring. Okay. And recall what we meant by symmetric means if X is in S, that means F minus X is not in S. So the gaps are actually F plus 1 divided by 2. Those are the ones that are missing in the semigroup. So symmetric ones are Gorenstein, so you have to have type 1 in the symmetric case. So the semigroup is almost symmetric. It's just another definition where it is instead of type 1, I have F plus the type divided by 2 is the number of gaps. We just want to do an example, say, if I have 7, 8, and 9, then this multiplicity is 7, embedding dimension is 3, and the gaps are, if precisely, I just have all of them up to 6, 10, 11, and 12 are not there. 13 is not there. 19 is also not there if you just looked at it. And 20 also, we cannot write it as a sum of these things. So this is it. So the Frobenius number is 20, the gaps are 12, and the pseudo-Frobenius elements, how are they figuring it out? Those are things that are amongst the gaps. Like 20 is the last one. So anytime I add any number like 7 or 8 or 9 to 20, it will be there because anything is there after that. But 19 too has the property. If I added 19 plus 7, it hits past 20. So it's there. And 19 plus all of them are there. So these are the only two numbers. If I took 13 and I add 7, I get 20 and it's not there. So these are the pseudo-Frobenius numbers. They are like the Frobenius number if you just added any of them, that it will be in the semigroup. That actually, the number of those is really the type. That's a type 2. So it's another way just looking at the numbers to tell the type. And this is a very special case. We know it is height to Cohen Macaualay. So beta 1 is 3 and beta 2 is 2. Another example, let's look at it, which is 5, 6, 7, and 9. It has multiplicity 5. The embedding dimension is 4. The Frobenius number here is 8. After 8, everybody is in there. And the gaps are 1, 2, 3, 4, the first 4 things, and then 8. So the genus is 5. The pseudo-Frobenius numbers are 8 and 4. 4 as well, because if I added 4 plus 5, it gets 9. And after that, everything is passed to the Frobenius number. The same example. This is almost symmetric because when I add Frobenius number plus this type 2 and divide by 2, I get 5, the genus. We'll see this. There's some reason why this is actually almost symmetric. It's part of a class. There's lots of conjectures involving these various invariants in the numerical semigroup. I'm not going to mention all of them. One of the most famous one is the Wilf conjecture, which says not that the Frobenius, it's a bound on the Frobenius number in terms of this. This is the numbers that is there. These are the gaps, and then n is the embedding dimension. A lot of computational and algorithms that are there using so far. There are many cases it's known. I'm just putting down one of the few things where it is known when the gaps are less than or equal to 100. This was 66, and then using some computational thing, it was extended very recently, I guess, to 100. Again, I'm not talking about the that conjecture. There is this conjecture called the width conjecture, which was first introduced by Herzog and Stamati, that says that the Betti number, the first Betti number, the minimal number of generators, is going to be less than or equal to the width plus 1 choose 2. We'll talk a little more about it. And it was extended to say, oh, I did it wrong in this, isn't it? So this one says beta t is less than or equal to width plus 1 choose t plus 1 for all of the other Betti numbers. It's in the same paper. They show it is true for e equals 4. The multiplicity is 4. Or if the width is at least 40, some big number. This has been verified for that. So one of the reasons why this width has come in a way is there was a long time ago a conjecture where Herzog and I were talking about it, which was later proved by Tan Wu, where if you have a numerical semigroup and you keep on adding the same numbers to it, the Betti numbers of that are eventually periodic. And therefore, and that it turned out, Tan Wu proved is true, and it is eventually periodic with the period, the width. And therefore, the width is kind of that way. Once you fix the width, then the Betti numbers at least, and then the multiplicity, the Betti numbers are, because the multiplicity is the first one, the smallest one, and width is the how wide it is, then we have a bound on the Betti numbers. And that's one reason too. That's why this thing makes sense. Okay. Now let's talk about Sally semigroups. So when E is bigger than 1, we take this one, E plus 1 up to 2E minus 1. Well, obviously, I won't go beyond that because it will no longer be minimally generating it. So these define a numerical semigroup of multiplicity E, and width is E minus 1. And it is true, it is an arithmetic progression. These semigroups are also called interval groups, as they are generated by all the numbers between E and 2E minus 1. And this is what this semigroup is. And now look at this one. This is the one E plus 1, and I'm dropping two things, E plus 2 and E plus 3. And then I have the rest of them there. This is called Sally semigroup. It is a symmetric semigroup, and so it gives you the semigroup ring is Gorenstein. Herzog and Stamatig first called it, and we'll see why. Why did it come about? Okay. In a couple of papers in 1980, Judy Sally completed the characterization of which embedding dimensions mu for Gorenstein rings of a given dimension D and multiplicity E will guarantee that the associated graded rings will be Cohen Macaualay. And she called such an embedding dimension is a good embedding dimension for a Gorenstein ring to have. And she proved there that these are D or D plus 1. D is now the dimension. E plus D minus 2 or E plus D minus 3. The semigroup rings, these are rings of dimension 1. So if I put D is 1, the last bit is E minus 2. Embedding dimension E minus 2 are constructed to prove the very last part of this puzzle, this whole theorem, showing that these are the four cases of good embedding dimension a Gorenstein ring can have. So in order to do that, this was the semigroup that is called the semigroup that I mentioned, E plus 1, E plus 4 to 2E minus 1. This was the semigroup that showing that it is good and has associated graded ring Cohen Macaualay. That was the final part of the puzzle in proving this problem. And that was one of the reasons I think Herzog and Stamatig found it interesting and called it the Sally semigroup. We call a semigroup a Sally type semigroup if it has multiplicity E and embedding dimension E minus 1. So as a convenience in notation, I will put this bracket A comma B to mean everybody between A and B, the entire interval. So Sally semigroups are minimally generated by a subset of E to 2E minus 1. So it is really a Sally type semigroup. We will use another notation for saying what is a Sally type semigroup. I write S with a subscript E with a T as a semigroup of multiplicity E that is minimally generated by just removing everybody in T. Actually, I think that is what I wrote, but I really don't want to do that. Let me change it. I want to remove E, and I is not in T, not E, okay? So everything in E plus I, that's what is E up to E minus 1, and I not in T. So for example, this Sally semigroup, what would it be? It is SE, where I remove E plus 2 and E plus 3. Okay. This is just for easy to write. So we call the semigroups and the semigroup rings of multiplicity E with E minus 1, all of them as Sally type. Okay. This is the same page, I think. Now, a semigroup minimally generated by E to E plus W for all positive integers from E to T, they are called the interval semigroups. Sally type semigroups are those carved out of the interval semigroups of with E minus 1 by introducing some gaps between E and E minus 1. So this kind of started in a WICA is standing for Women in Commutative Algebra. So there was a meeting in the summer of 2024, which is when I started a project, and it is with Priya Dubey, Kriti Goel, Neil Sahin, Srishti Singh, and myself. So I'm going to say this as DGS cubed, and we continue this later on, and Priya is not being part of it now because she's decided she will leave academia to go to industry by after this. So she thought this would be a different kind of things that she should be working on. So what did we do? I take in this one just to continue, they want to generalize what the Sally semigroup, which I mentioned was 2, 3. So we removed two things, M and N, from this whole thing, E to E minus 1. I call it Mn. And afterwards, we thought, well, why pick only 2 just because it was left out in the case of the Sally semigroup? We will just, as long as we did that after we finished, we thought we might as well take care of this when you just get rid of one element instead of nothing. Okay. So we will go in the reverse order, and I will first see what this SEM, which is the embedding dimension E minus 1. For instance, it's not so difficult to check that the Frobenius number and the Cohen Macaualay type in these cases, the Frobenius number, when you remove M, if M is 1, it is 2E plus 1. Otherwise, the thing that we removed, the new gap introduced, E plus M, is the Frobenius number. Everything after that is there. And the type is actually 1. If I removed 1, and removing E minus 1 is kind of cheating, because when you remove E minus 1, the width changed, right? It becomes E minus 2. So, but anyway, I just put that in because if you put one number to remove, E minus 1 can be removed and it will still be Gorenstein, because it becomes an arithmetic sequence of the type that I mentioned, where the multiplicity is 2 modulo n minus 1. In this case, it was E minus 2. E is 2 modulo E minus 2. If it is any other number, the type is E minus some. It's pretty big. You could actually check because this will be the pseudo-Frobenius numbers. So in any case, let's not worry about that now. SC of M is symmetric if and only if M is 1. And if you choose to use E minus 1, we put that in. And it turns out it's almost symmetric otherwise, because if I added these guys, that E minus M, and to the type to E, then I get 2E, which gives me E as the number of gaps in this particular case. So this is for SEM. Now let's go to embedding dimension E minus 2, where things are a little more interesting. So the first thing, well, maybe not the first thing, but anyway, I will write it in this style. So the Frobenius number of SEMN is 2E plus 3. This is the case, remember, this is the Sally semigroup. And this M equals 1 is rather strange and special when you remove the first one, E plus 1. And otherwise, it is E plus N, the Frobenius number. We will see this M equals 1 is always going to be somewhat of a special case. And the type, again, see, already you see, when I remove the 1, it's kind of strange. But let's, if you don't remove the 1, E plus 1, but remove everything else, this is the Gorenstein one, where the Sally semigroup. Otherwise, the type is E minus N plus 1 and E minus N plus 2. It's because what are the gaps? I'm going to, the gaps are E minus 1, and then, which I think you can see here, is E plus N. Right, that's it. And then what is the pseudo-Frobenius in this case? the pseudo-Frobenius numbers are going to be from n plus 1. Maybe I'll just write that pseudo-Frobenius ones, or n plus 1 up to e minus 1. And then I'm going to have this e plus m, which is not there. But then I add anything to it, it is there. And then in this particular case, when n is bigger than m, I'm going to get an extra number, which is n is bigger than 2m. This n minus m will be an extra one. And that's what makes it a little extra, the type to go up by 1. In any case, this tells me that this SC of Mn is symmetric if and only if Mn is to 3, that we noticed, right? Otherwise, it's not symmetric. Okay. So this is what we actually set out to do. So that's why I called it the main theorem for the embedding dimension e minus 2, and then the other things were afterwards. We wanted to just compute the minimal generating set. The minimal number of generators are e minus 2 choose 2 if it is one of these guys. It is e minus 2 choose 2 minus 1 if it is m equals 2 or say n bigger than or equal to 6. So 4 and 5 are missed out in here. That's because they are showing up here. And otherwise, this is the generic case, e minus 2 choose 2 minus 2. I put this down because initially we wanted only to compute the minimal generators, all the minimal generators which we did. But this is important because after you write down the these are the minimal generators, say by guessing or otherwise, you want to know that that's it. And this is the main theorem for that reason. So I'll talk about why it is. This is the generic case. This is a case where and this is not true. That is, m is bigger than or equal to 3 and just not equal to 3, 4. Okay, where the minimal number of generators is this. So this actually verifies the width conjecture because the width is e minus 1. So it is easily achieved because you want to have this to be e choose 2 and all our things are e minus 2 choose 2 and something less. So it is clearly satisfied. It's also true for this, right? In this case, it is actually e choose 2. When it is the empty set, nobody is removed. So the width conjecture really states that Bi is maximal for the interval semigroups. That's the point of the width conjecture. You take the whole interval semigroup. So the way we first proved this one, the minimal generating set, which I will write later on, is to show that this is the minimal number of generators. And for that, we are using this rather old theorem of Hofstrom, which says that for every one semigroup, lambda in the semigroup, you have I'm going to just use the simplified version that we need for just finding the minimal number of generators. Lambda in S, we associate a simplicial complex. And what is a simplicial complex? Well, it has the R-dimensional face F, which, remember, I'm starting with I0, so R plus 1 of there. If I subtract all of them, it is in S. So associated to every one of those delta lambda, there is a complex. That is, I can have a map delta R, which takes F and sends it to, in a way, you will have like this Koszul complex, minus 1 to the J, Fj, where you just remove the jth one, and that's the one that A minus 1 to the J, the obvious map that you will write in some sense, the natural one, and that gives you a complex. And the formula is the beta 1, just for beta 1 we are talking about now. It is true, there is one, the same thing will, I just change this 1 to I will have a formula for beta I. That's the theorem of Hofstrom. So I just wrote a special case here because that's all we are going to do. So we compute all of those beta 1 lambda. For all lambda in S, it sounds like a lot of them, but most of the time it's going to be 0. That's why all lambda in S is just this homology at the 0th part. So That's really the one that I start. I'll have an example later on, which tells you what this might be. So I only need to compute the one that is there. Let me call it C1, the degree. These are the ones. And then I say C0 and C minus 1. That's because we are offsetting it by 1. So this is the delta 0 and delta 1. So I'm just checking on how many of these guys are not going. So then that is the rank of, let me call this one C1, rank of this. Sorry. How do I erase this? So rank of this minus 1, because that's what it's going to be, and then the rank of delta 1. Oh, I wanted to do this other way, I think. Sorry. So these are the things that will have 0. So these are things that will be just singletons, singleton. And these will have 2 elements in it. Okay. What we did was we carefully, I underlined the carefully because that's why the calculations are horrendous, calculate this for various lambda and see that beta 1 is what we say in the theorem. In fact, Kriti actually, in the while doing it, has written a gap code that computes this beta 1 lambda, if you just input the appropriate things. So let's just quickly see an example, 6, 7, 8, and 11. So this is E is 6. And then I'm leaving out as 6. 6 plus 3 and 4 are out. Right? That's what this is. Okay. So all of the other lambdas besides these, you will get 0 because they will be exact. So let me just do one of them, for instance. Let's take 18. If it is 18, I could subtract from 18 7, that will be there. I can subtract from 18 11, that will be there. I can also subtract 6, that will be also there, right? In this case, this is, I'll just remove that 18. We remember 18. So for 18, for 8, I don't know what I did here. Something else happened. Okay. For 18, these are 3 things that will be in C1, right? These 6, 7, and 11 are possible. And then this side, I can only have 7 and 11. And this, of course, there is this empty set there. So what am I going to have here? So this is 1, and this is rank 1 and 1. So I'm going to have homology 1 in this part. And that contributes 1. And 24 will also contribute 1. Let's just do 24 just to check what we are talking about. There I'm going to have 6, 7, 8, and 11. All of them will be there. And then here, only a few of them. Not everything is going to be there. Out of the 24, I could have 6 and 7. I can't have 6 and 8, but I can have 6 and 11. I can't have 7 plus 8 because 15, and then I'm getting a subtracting 15 from 24 is 9. But I can have 7 and 8. I can't. And then I can have 7 and 11 because that will give me 6. And that's it. And one more thing, 3. I could have 6 plus 7, 13, plus 11, 24. And then I just take out and see that I have a homology 1 over here. And that's why 24 contributes to 1. So you just compute it all, and you get that beta 1 lambda is various things. And so I have R6. So if you compute it, in this case, we actually can get the entire resolution, R6, R8, and R3. I say that because we do compute the resolution for when you have E plus 3 and E plus 4 removed, because it's a very special case. It's not the generic one. So here is what it looks like explicitly, all of the, for various cases. I put these down as a J and a K with the various things written, where this is the ring. I don't know why this is coming up. The ring KXI. Sorry. Okay. I don't know. Anyway, let me finish writing it and then it'll go away. KXI, degree of xi is e plus I. So they won't all be there. So xi's will only be there that, for instance, xm and xn are not going to be there when I remove m and n. So this whole thing will be there whenever it makes sense. Okay. I'm not writing down the whole thing. Our method of proof was that these are minimal generators because they cannot get rid of them, and they are right, the correct ones in number. That was the method in that case. Oops. Let me move. In the next one, we finish the rest of it because remember, e plus 1, we never considered it because it's a very special, it's a strange case. So we do that in the next one just to finish it off, like because we did SE of M. Using singular, which is what Neil Sahin was using because she's in Europe and they use singular on Macaulay, not Macaulay too. So she asked me, because she was computing various Betti numbers as part of the thing. And we have a bunch of conjectures. Not, because they have a really interesting part. This is the one that I want to emphasize. This m and m plus 1, that is if two numbers are next to each other, consecutive numbers like 2, 3 and 3, 4, that we were they are going to be special. Such numbers, they, when you take it, they seem to be, the Betti numbers are actually the same after a while. They have lots of things in common. Also, if I just remove 2, like in the case of 2, 3, and then something else, as long as it's not 2, 3, 2, 4, and 2, 5, we're much beyond, they're not immediately, then they seem to be close. They approach the Betti numbers of 2, 3, the Gorenstein case. They won't be there because, that is to say, let me show you. Up to the n minus 5, the tail is going to be different. And for a while it is different because after all, they are not Gorenstein. So the type's wrong. The last part of the resolution will be different. And we saw this, we did construct a resolution for this, SC34, and they have determinant of Betti numbers. Another conjecture is that 2, 4 and 2, 5, which are not going to be like the 3, 4 in any way, except that their Betti numbers should actually be the same because the first Betti number is actually equal. And it turns out all the examples that we have computed, the rest of them are also true. Because it's not like even though we used the computer, it didn't compute anything like hundreds of examples. So just computed maybe 10, I think, at the maximum. So I do not know. But it seems to be right all the way through. I thought we were going to show, let me show this, and maybe, are we going to take a break? Then maybe this might be not a bad idea to take a 5-minute break.
Yeah, I think you decide when to take the break and just tell us.
Let's take a break at this time, okay?
All right.
So I'll have some tea too.
Any questions at this point? Any comments? All right, so we're taking a 5-minute break and we'll start at 6:16.
Okay. Okay. Oops. I don't know. I want to move to the next one. Okay. So this is another way to also do. I'm not saying it's necessarily any faster, but maybe it will look, there will be an illusion of being faster, is that if this ideal, and also there is other reasons, this is nice. The ideal of SEMN, that's IEMN, I'm writing, let me put that in here. For here, I've just seemed to have changed because it's just too many things. SEMN, the ideal of SEMN, I'm writing it as I with EMN. And there's a reason I put this E in the superscript, we will see, okay, later on, because there is a confusion with the subscript later. So this is one of the reasons confusion. See, if I put this I2, this 2 is the 2 by 2 minors of this matrix. Okay, not the E, the multiplicity. That's why the E goes up in the new superscript now. So I take this matrix. What is this matrix? This is what you would normally have x0, x1, x1, x2. And then since we are leaving out m and n, I don't have xm. So I won't have xm minus 1 xm because there is no xm. And then there is no xm, so there is no xm, xm plus 1. The same thing here. So this is AMN. And then I have BMN, which is just this matrix. And look at this matrix, just so you know that their 2 by 2 minors are in the ideal of the semigroup. All you need to know is every number in the second row is the difference between the second row and the first row in the subscript is the same. 1, 0, here it is 1, and here it is 2. Anytime you do that, the 2 by 2 minors are going to be in the semigroup. And that's true, but I picked this particular BMN in this case. This is an M is not 2, this is the generic case. M not equal to 2, and MN is not equal to 3, 4. Of course, this has more things in it. But I have written these guys in blue, 2 things in blue. These are the 2 columns. It is true that the ideal is a 2 by 2 minors of AMN plus 2 by 2 minors of BMN. But if you took all of the 2 by 2 minors of AMN and those 2 by 2 minors of BMN, which involve these 2 columns. So this column and some other column, and this column and some other column, they are the minimal generators. And we write it down and check that they have the right number. Well, you just have to check how many columns are there in this, right, of the matrix. And it is not just in the generic case, the special cases, they look a little different. The only case that's a little bit of a problem, this is the case n bigger than or equal to 6, this B2n. I will have this matrix B, and then there's one guy that won't be there, and that's this one. One extra thing. Because remember, in this case, you had a strange, the minimal number of generators was 1 more than the other guys. And that's the reason it is. And 2, 3, 2, 4, 2, 5, and 3, 4, they're all some other different looking matrices because they are special name numbers. Because this M is very small, something interesting is happening there. And in these cases, the numbers being small, something slightly different is happening. And you get a different matrix. So there is this method of writing the thing. Why is this actually true? So here is the thing. And I say, see, this is an illusion of being short, because look at that, it is only 1 page. What it is that I'm using this theorem, or a trick by, it's something that you can prove, but it is a theorem of a former student of Kuntz in his PhD thesis. Gastinger did something for the numerical semigroups. And what it is that whenever I take some other thing which are in the ideal, and if it turns out when you mod out by let's say x0, the first one, so you get a vector space, and they both have the same dimension, that we know if you mod out by I, it will have dimension E. And if this J, when I mod out by x0, also has a dimension, vector space dimension E, then they are really the same. So that you should, it's more, it's just on something on the rings and ideals that you show. So look at these guys. When you look at it modulo x naught, forget about this one, look at this one. Everybody will be there except this x1, xm minus 1. So we need to add that x1, xm minus 1 and x1, xn minus 1. And then once you added that, the rest of them are going to be there linearly dependent because they will not in a vector space. So my vector space will have all of the 1, of course, as a basis, and all of those xi's not equal to m and n, and these two extra guys, x1, xm minus 1, and x1, xn minus 1. You can get it mostly by looking at AMN in this particular case, the generic case. And BMN is, of course, needed. And then I know that since it is E, there's a part of it that you will need for that. The reason we need that is you also want to say all other products such as xi, xj, or if I have x1 squared, xm minus 1, those are all in there. Because that is something that is as a vector space. So anyway, some more computation and checking needs to be done. Then you can show that it has dimension E, and that's why this is this determinantal structure is possible, not the sums of two determinantal ideals. That's how I write this, the ideal, and similar to this. And now I want to go back to the question we started with saying about the Gorenstein. When are these guys Gorenstein, right? So we already saw when you put this only one thing, it is Gorenstein if you removed 1, and then this cheating case E minus 1 is cheating because of width changed. And then in the case of Mn, it is symmetric if and only if it is this 2, 3. Remember, that was what we did. And now, so we can ask when are the Sally type semigroups at least symmetric? We've already done this for E minus 1 and E minus 2, where it was 1 and 2, 3. So I'm going to now consider the embedding dimension E minus k for k bigger than or equal to 3, I say, because we've done it too. So let me take this class. E bigger than 1 and k, let's just say E by 2, it's okay. K is between 1 and E by 2. 1/2. I'm going to put this E I told you in the superscript because I'm going to have symmetric algebra, which will have a subscript, and there'll be a serious confusion. So I put an E up there. So SE of K is a Sally type semigroups generated by removing K consecutive numbers from E to 2E minus 1. So let me say Sj now for K. Don't worry about the J being in the superscript, it will go away. For now, I start with the E, and then I'm removing everything from SE plus J, K of them. So I removed E plus J plus 1 up to E plus J plus K minus 1. That's K of them. Those are the new K gaps I've introduced. They are consecutive graphs. So since I'm only talking about K bigger than or equal to 3, I'm taking E bigger than or equal to 5. Again, when E is really small, in small cases, some really things need to be done. Many things you could just say E, and it will eventually be good, but we could take E bigger, a little more if you want it to be too. Not a big, not so much is lost. And I won't write this E, which is the superscript, when we don't really need to worry about it. So here's a theorem, which I will show. If E is at least 4 and K is less than or equal to E by 2, this guy is symmetric if and only if K is J. So the reason I say K less than or equal to E by 2 is if I started from K and then I have to keep on removing K plus 1, if it is K is bigger than E plus 2, I can't. There is not enough, right? Because I can only go up to 2E minus 1. I want this to be available. And that's the reason k is less than or equal to e by 2. This whole thing won't make sense otherwise anyway. So I say Sjk is symmetric if and only if it starts at j. So this is the first thing with the 2, 3. Remember, when we were removing two things, the only time you will be symmetric is if you started from 2. Otherwise, it's not. So if you are removing three things, the only time you will be symmetric is if you remove e plus 3, e plus 4, and e plus 5, and nothing else. And that's what this is saying. And it's true for SE1. As long as you are insisting on keeping that e minus 1 as your width, the only time you will be symmetric is if you removed 1. So what is the proof for this? I think maybe I am thinking, how long am I going from now? Is it till, how much time do I, maybe I think another 10 minutes or something, right?
Yeah, it's been an hour, but I mean, you can surely have 10 more minutes.
Okay.
Just go ahead.
Yeah, even 15 is fine.
All right. So let me just quickly say as to why this is true, that it is. To show that it is symmetric if and only if this is true, I just have to decide what the Frobenius number is. Well, what the Frobenius number can be. I may not even have to do that. And say that the number of gaps is, unless it is this case, j equals k, the number of gaps is not exactly half of f plus 1. That's all I need to do. So let us consider the gaps. These guys are clearly gaps, e1 up to e minus 1. And these are the new gaps I introduced. So I already now have e plus k minus 1 gaps. And then after that, we see that 2e to 2e plus 2j minus 2 are there because those are the ones when you have e plus 1 up to e plus j minus 1 there, all those sums are going to be in there. So if I looked at this, as long as j is bigger than or equal to k plus 1, I am not going to have it to be symmetric because I already see that this difference is e. So my Frobenius number is e, this last one, e plus j plus k minus 1. The last gap is the Frobenius number if j is bigger than or equal to k plus 1. And then that certainly add 1 to it, e plus j plus k. That's not twice this number. So it's not symmetric if j is bigger than or equal to k plus 1. So I have to see what happens if j is less than or equal to k. In this case, you have some gaps, extra gaps. For instance, this number 2e plus 2j minus 1, it's not in there. That was the number. That was the next number. Remember, 2e plus 2j minus 2 is in there. But this number, next number is not there now. Not only there, none of these guys, the next set of them, t here, they are also not there. T plus one of them here, not in there. So the gaps are at least this much. These extra gaps are there. And the Frobenius number is, at least if j is, this requires some work. So I'll just put that in, not a lot, but you have to be careful and work something. And know that when j is bigger than or equal to 2, this is the Frobenius number. Since this is the Frobenius number, in many of these, once you got it, you should be able to check later on. And I get this is only symmetric if twice this is this plus 1. Divide, right? So I just take twice this is this plus 1 here. That happens exactly when k equals j in this case. And then, of course, what about j equals 1? We know that 1 is a very special case, so we better check that. So in that case, again, these are the same f and g, the Frobenius and the gap. And so you can't, this equation is still be valid. Unless, of course, this e is 2k. When e is actually 2k and j equals 1, f actually is this one. 3e plus 1 is the Frobenius number. And it is, the gaps are 2 times e. It can only happen j equals k equals 1. It's a very special. Nothing's happening. And e is actually 2. This is really not a case that even exists, right? Because we've already thought e bigger than or equal to 4. So this is the reason the theorem is true for that. And it has this ideal thing, very nicely set up. This is the ideal I have to say what these things are, but there is a determinantal structure for this, which maybe I will just not say what it is now. I have written this as what this is a 2 by these two matrices, and they take the 2 by 2 minors of this, and the minimal generators are the 2 by 2 minors of this and the 2 by 2 minors which has the blue column. But all the other 2 by 2 minors are also in there. So you can write the minimal resolution. It is very similar to the symmetric case of the arithmetic sequence, or that, yes, the Sally semigroup, which we also wrote. What we do here is we look at this matrix A. This is generic, even though it doesn't look like it. It's got the generic height. It has got the generic height because it is the numerical semigroup coming from an arithmetic sequence of where E is congruent to E minus 1 mod 2. E is congruent to 1 mod the E minus 1. And that's the reason it is generic. And so I take the Egan-Northcott resolution of this guy. Okay. So I put that in. And then I flip it. That's also true. So I take this Egan-Northcott resolution of A, which will resolve I2 of A. And then I take the dual of it, which is also exact. And then I write this complex map of maps from E star to E. What is that? The last one is a symmetric algebra on the two things by E minus K minus 3 of size E minus K minus 3. So I have E minus K minus 2 generators in this. And those are precisely these E minus K minus 2 things that come from B. You can't just put them starting from the beginning. You have to count them from the end where it hits. Somewhere along the way, E will come. After that, what happens is where the first place to start, you judiciously define the first one, and then it becomes a map of complexes, the psi. And then I just take the mapping cylinder. It is going to be symmetric because it's going from E star to E. And that is the resolution of my Gorenstein ideal, this Gorenstein ideal, IE of K. So you can compute the Betti number since you know the resolution. And I will end with just showing that these Betti numbers are, there is also another expression of this. We have one expression in binomial coefficient. You can simplify to get some other expression that looks perhaps a little better than this. And maybe not as, this one is easy to understand why, because this is coming from the E and this is coming from the E star. So I'm at, and this is the number of Betti numbers. So anyway, let me stop with this and thank you everybody for listening.
Any questions, any comments? Right, it seems there are no questions. Let's thank Hema for the really very nice talk. Thank you.
Thank you.
Thank you.
Thank you.